Welcome back, everybody. This is Earth and Space Science 102. My name is Stephanie Welch, and today we start talking about stars. This is part of a 4-part segment on our sun and other stars out there in the universe. So we'll need everything that we covered in the last couple of lectures, lecture 17 and 18, the 2 lectures on light and distance, all that kind of stuff, to really understand and apply to how we understand our sun in particular and other stars. Starting today, what we're going to do is first analyze our own star, and that is a really, really important point to cover first off. Our star, our sun, is really no different than all of the other stars out there in the night sky. In fact, it's kind of mediocre in comparison to a lot of the other stars out there in the night sky. The only reason why it's so impressive, why it completely dominates our daytime view, is because we happen to be right on top of it. As Carl Sagan said in the original version of Cosmos in the 1980s, all of the stars out there are suns, and our sun is just one of those many, many, many stars out there in the universe. And he talked about how that was a really grand realization for him as a kid, that our sun was really no different than all of those other stars. So today we'll talk about what our star is, how it initially formed, how it continues, and what its overall lifespan looks like, what the internal structure of the sun is, and what solar weather is all about. From there, we'll go on to talk about other stars and how we classify those stars by comparing them to our own. That'll be the next lecture, lecture 20. And then we'll go on to talk about the entire lifespan of low mass stars like our sun and high mass stars that have even more brilliant and amazing outcomes. So let's dive right into it. First off, our sun. When you actually look at what it is, when you actually think about what it's made of, what it's doing, and why it's special, why it shines, all our star is, all our sun is, this object that is so incredibly massive that it's holding the rest of the solar system in check and in balance. All our sun is a ball of hot gas bound together by gravity. It's almost entirely hydrogen and helium with only trace amounts of all of the other elements, stuff like calcium and potassium and so on. So it's really no different in that sense than a lot of the other objects out there in space, even our own planet and our own body. It's all made up of the same basic elements. Except in the case of the star, you have a lot more hydrogen and helium just because it's a really big, massive object and has a much higher escape velocity. It's an incredibly hot object that we already know, and that's why it glows. That's why it's colored yellow. It's because of its immensely high surface temperature. But if you think about the one heartbeat of our star, the one big process that continues to keep it going, it's this idea of what fusion is. So every second in our sun, and we think that our sun has been around for about the same time period that our planet has been around in the rest of our solar system, about 4.6 billion years. So every second of every day for 4.6 billion years, our sun has converted 600 million tons of hydrogen into 596 million tons of helium. So it's an incredible energy balance. That's an incredible amount of material that you need just to power an object like our sun. But the big question you should be asking yourself right now is, if you start off with 600 million tons of material converted into 596 million tons of something else, then there's a little bit lost in that balance. There's a missing 4 million tons of material left to be accounted for. So those leftover 4 million tons of material are converted into pure energy in the form of light and heat that fuels our planet, makes it possible for life to be present on our planet. So our sun is not some object that's on fire. If it were only on fire, if it were consuming oxygen and going through combustion, then it wouldn't be hot enough to even heat up the surface of the planet Mercury. That kind of heat wouldn't translate through space. It would be nowhere enough to really fuel the surface energy and heat balance of our own planet. In order for our sun to be converting that much material into energy, it has to be doing something far more impressive and far grander than just being on fire. Our sun is a thermonuclear furnace. It's a fusion reactor, basically, under these incredibly high temperatures. And we know from earlier on in the semester that all temperature is the average kinetic energy of a substance. Under the incredibly high temperatures present in the very core of our sun, energy can be converted into mass. Mass can be converted into energy. E equals mc squared. This incredibly simple, very concise formula that Einstein wrote in 1905 explains how our sun works and how it's powered, what its heartbeat is. And as long as that process continues, then our sun will remain stable. So the way this works is that E stands for energy, M stands for mass, C stands for the speed of light, and that is a constant that's squared. Right? So what that means is that as mass approaches the speed of light, as mass moves around extremely fast under very, very, very high temperatures, that mass can be converted into energy. And that's exactly what happens. That's exactly how 600 million tons of material is converted into 596 million tons of something else. Hydrogen is converted into helium. Something small is converted into something a little bit bigger. And the sun and the entire solar system remains in balance. Most importantly, if it's going on in our sun, it's going on in every other star out there in the universe. So to further understand this and to kind of look into this idea of what fusion is and how it works and how it balances out processes in the sun, we have to take a couple of steps back and look at the basic set of particles that make up the atom. Some of which are almost going to be completely ignorable from our vantage point because we're looking at processes inside the sun. So as you probably remember, there are three basic particles that make up an atom: electrons, protons, and neutrons. Under these incredibly high temperatures, we can almost completely ignore what's going on with the electrons. They don't really play into how this is really going to work. Let's concentrate on the nucleus of the atom, making up far less than 1% of the total amount of space within the atom. This is where all of the actual mass lies. All of those electrons are just all ephemera. They're all charge and no substance. So the nucleus is made up of protons and neutrons. And those protons contribute to its atomic number. In fact, that atomic number for a particular element is just the number of protons it contains. The number of protons plus neutrons equates to its atomic mass. And that has to be, on the perspective of a single atom, a whole number, 1, 2, 212, for instance. But on the periodic table, you'll see it written out to a series of decimal places, because that's all known versions of that particular element with different numbers of neutrons. And these versions of the elements we call isotopes. Okay, so far we know that those protons and neutrons are going to be really, really important. That's what's going on in the central part of the atom. For the element hydrogen, the most abundant element in the sun, all you really have is a single proton with an electron floating around it that we can basically ignore for right now. So that single proton is really all that is making up the mass of something like hydrogen. And under these really high temperature conditions, those protons are moving around so quickly that they can combine together and make up a slightly heavier atom as a result. And when that happens, you have to start adding up the number of protons to see what element you end up with, adding up the number of protons and neutrons to end up with a particular mass for that element. So fusion is the process of taking these tiny little particles, the mainly protons and neutrons in the nucleus of the atom, and combining them together to make something bigger. If you fuse two things together, you essentially glue them together and you make them one. 1 + 1 is 2, 2 + 2 is 4, and so on. Fission is the opposite of that, and that's the far more common nuclear process that most people are familiar with. All the way back to the beginning of the 20th century, we were having dilemmas and we were having quandaries about, should we split the atom? Should we create nuclear weapons? Should we power our homes through nuclear factories and so on? And most of that energy is derived from not combining particles like the sun does to create energy that way. It's energy derived from actually splitting the atom. So to undergo fission is to take the nucleus of the atom and split it apart. There are incredibly immense forces, strong and weak nuclear forces that hold the atom together, so that when you split it apart or when you add particles together and make up a new atom, you create an incredible amount of energy as a result. So fission is the process of taking a particle, splitting it, making up something smaller. 4 divided by 2 is 2 and 2. But fission is not going to be something that happens really with any kind of frequency in the sun. The sun is going to be powered by fusion. So nuclear power plants, the vast majority of nuclear weapons are powered by fission. Fusion is something that's going on within a star under extremely high temperatures. And this is something that happens completely naturally. We have no control of it. And we certainly don't have any sort of way of creating those kind of conditions currently on the Earth's surface to derive energy that way. If we could take even a tiny fraction, 1% of 1% of all of the energy that's formed this way through the sun and harness it, we would have untold amounts of free electricity for the entire planet. Burning fossil fuels would certainly be something of the past. So the way this works in the sun is that under these incredibly high temperatures, so you have to have some mechanism to get you to these threshold temperatures of 3-4 million Kelvin before these particles are moving around so fast that they're no longer repulsed by each other. So you kind of have to think about all of these individual atoms as having somewhat of a personal space bubble. Maybe kind of like you walking around a crowded hallway or a crowded mall or something. As you walk, you sort of naturally assume a 2 or 3 foot personal space bubble between you and all of the other strangers around you. Atoms essentially do the same thing. As they move around, they are repulsed by each other through electrical forces. Under high enough temperatures, they move around so fast that they can actually exceed that tendency to have that personal space bubble, and they move together and combine together and become one. So, for instance, if you had 2 protons and they come together, you would end up with something that instead of having 1 proton and being hydrogen, it would have 2 protons, and it would technically be helium. In order to really make helium, you wind up having to do something a little bit more elaborate than this. You also need some neutrons thrown into the balance as well to make up a stable resultant particle. But under high temperatures, and only the kind of temperatures that you get under these incredible conditions, like the moment of the Big Bang, and in the core of stars, and in the death throes of stars, those are the kind of conditions that you have high enough temperatures to actually have fusion occurring naturally. Now, the way that our sun and other low-mass stars, and having low mass and high mass stars is a little bit disingenuous because it really works on a gray scale. But it's kind of like taking everybody in the world and putting them into one of 2 categories. Either they're fat or they're thin. But let's just go with this for now. Having these 1 of 2 categories, high mass stars and low mass stars, our sun would have to be thrown into this category of being a low mass star, a fairly dim, meaning less luminous, a lower temperature star than some of the rest of the stars out there. The way that low mass stars are going to go about converting hydrogen into helium is through this process called the proton-proton chain. In this process, it actually takes 4 hydrogen atoms, and all those hydrogen atoms are really just a single proton. It really takes 4 of those to come together to make the equivalent of 1 helium nucleus. In chemistry, it's called an alpha particle. Along the way, through a series of reactions, a couple of those protons are going to be converted into neutrons. So what you wound up with is a particle that consists of 2 protons and 2 neutrons. It has an atomic number of 2 and a mass of 4. and that makes the element helium, this incredibly stable element. And further subsequent fusion reactions utilizing that helium can build up even heavier elements. But that's not something that a star like our sun is going to want to do, at least not until it runs out of hydrogen. So every second in our sun, 600 million tons of hydrogen, consisting of all of these little protons, come together through a series of reactions and are converted into 596 million tons of helium. Then you have this leftover material, the rest of the 4 million tons of material, and that's converted into energy. Energy in the form of things like gamma rays and particles that are going to leave this reaction entirely. So what we're going to do now is kind of go and take a look at this. We're going to look at what this ends up looking like in a step-by-step animation. So if you're kind of taking a look at all the details here, all of the protons that go in and out of the reaction are going to be pictured in blue. They're the big blue balls in this picture. The red is going to be the neutrons. So all the red balls in this picture are going to be neutrons. They don't actually contribute to the atomic number of the particle, just the mass. The yellow are going to be these things called positrons. It's the antimatter equivalent of an electron. That's basically something that you can ignore. You also have these gamma rays, so actual wavelengths of light, very, very short wavelengths of light that are produced in some of the steps in this reaction, and these things called neutrinos. That's another antimatter particle, and these neutrinos are going to be important because we can actually count these neutrinos. This is how we get an idea of the rate in which fusion occurs in our own sun, is by figuring out how many neutrinos get produced. Okay, so now that you have sort of the basic layout for this, I'm going to restart the animation. And what you can see here is starting out with 4 protons. So it's the proton-proton chain. The 4 blue balls in this picture are the 4 hydrogen atoms. They first come together, 2 at a time, to produce sort of a weird form of hydrogen with a mass of 2. And you also produce neutrinos in that reaction. Then they come together with eventually 2 more protons, and you get this weird version of helium that's kind of unstable with a mass of 3. You lose a couple of protons along the way, and what you ultimately end up with is 2 protons and 2 neutrons. So all of the really nitty-gritty details are not something that I expect everybody to completely process, and take away from this. The most important thing is that you go into the reaction with 4 protons, and you come out with a mass of 4. Except 2 of those protons have been converted into neutrons. That's where those positrons, the yellow balls, are created in parts of this reaction. So that's how the low mass stars do it. And the way this works is that process of taking those 4 protons and converting a couple of them into neutrons winds up being a fairly slow and almost inefficient way of going through this process. Now, it sounds plenty efficient when you take into account that this converts 600 million tons of material into 596 tons of material every second in the sun. But when you kind of take a step back and you compare it to how high mass stars are going to undergo the same process, it's going to seem a little insufficient in comparison. The way that high mass stars do the same thing, and we'll continue talking about this, we'll come back to this a little bit later when we go on and talk about high mass stars. The way that high mass stars do this is by using heavier elements as catalyst in the reaction. All you're really doing is starting out with something heavy and continuing to add a proton to it, increasing the mass, and sometimes also increasing the atomic number until you're able to spit out of the reaction essentially a helium nucleus. This is called the C&O cycle because the heavy elements in play here are carbon, C, nitrogen, N, and oxygen, O. So using carbon, converting carbon into nitrogen, nitrogen into oxygen, spitting out the helium nucleus and starting over again, you do what the low mass stars do. You just do it a lot faster, a lot more efficiently. And another way of thinking about this is that this means that these stars are going to have a lower overall lifespan because they run out of fuel a lot quicker. So if we kind of take a step and see what that looks like in the animation, then we'll see that what you are ultimately doing one step at a time here is starting with carbon with a mass of 12, adding a proton to it, and adding that proton increases the atomic mass from 12 to 13. And that proton's converted into a neutron, so that changes back into carbon again, adding another proton, converting carbon-13 to nitrogen-14, adding another proton, going from nitrogen-14 to oxygen-15, and undergoing another conversion where you take a proton and convert it into a neutron. And then finally adding one last proton, your fourth proton, and converting that nitrogen with a mass of 15 into oxygen-16. And what's sort of hidden in the step here is when you take that oxygen with a mass of 16 and subtract out 2 protons and 2 neutrons. What you do is wind up back where you started again. You go from 16 as your atomic mass to 12. So you go from oxygen to carbon again, and you start all the way over. Again, the most important part of this reaction is you're taking 4 protons, and through this whole messy set of reactions, you're converting that into one helium nucleus. Along the way, you're just using carbon and nitrogen and oxygen to get you to that final step of spitting out the helium nucleus. And the most important thing to remember about this is that it just works a lot faster. It's a lot more of an efficient use of your hydrogen if you're trying to use your hydrogen as fast as possible, by that definition of efficiency. Okay, so going back kind of to the the regular slides and the regular pictures here, and coming out of those animations, you can see how this fusion process is already going to become really important, because this is the source of energy in our sun and all of the other stars out there in the night sky. It's not just going to be the source of energy, it's also going to be the source of balance. The entire reason why our sun hasn't imploded in on itself and turned into a black hole, or exploded and taking us out with the process, the whole reason why our sun is this stable object, and we think it has been for about 4.6 billion years, is because of this process of fusion. So fusion doesn't just create energy, it creates an outwards push. This outwards push that's going on because of the force of fusion combats the internal collapse of gravity. And all our star is, all our sun is this object that's caught between these two opposing forces. It's kind of like having two different people pull you in two different directions. If the tug of war is equal, then you're not going to go anywhere. You're going to stand in place while these two people tug you in different directions. In our sun, the gravity crushes the star inward. And in the beginning, it crushed all of this matter inward to the point where temperatures in the core were hot enough to start fusion. Once that started, then the crunch ends, the gravitational collapse ends, and then fusion is this outwards force that gets created that stops it from crushing inwards any further. So the pressure exerted outwards by the force of fusion and the internal crunch of gravity are perfectly balanced against each other, at least for now. Now, much, much later on, towards the very, very end of our star's lifespan, our star's going to run out of hydrogen. It'll have to swell in order to reach high enough temperatures to go on to the next subsequent form of fusion, where it utilizes all that helium that's built up over time. That's when things are going to get really interesting, and that's when the star is really sort of out of balance. But for now, it's in balance because these forces are equal but opposite to each other. And as long as there's still hydrogen in the core of our star, it will remain in balance. We think our star has another 5.5 billion years of hydrogen left to keep this process going. And so that's what I mean by gravitational equilibrium. Gravitation is balance. It's equaled out by this outwards force of pressure. So not only does this create balance, it creates sort of the equivalent of a thermostat in the sun. All stars, we think, are balanced out like this. And the way this works is that if, for whatever reason, fusion just kind of got a little out of hand in our star, if for whatever reason, let's say we just ramp up core temperatures by another 1,000,000 Kelvin, then fusion would start happening at a greater rate, and the core of our star would actually expand. And by expanding, the entire sun would expand a little bit. And it would then, because it had expanded, cool off a bit. What this would do would give gravitation, it would give the force of gravity license to take over and to push back on the sun, collapsing it inwards a little bit more. By having gravity collapse inwards a little bit more, this drives up temperature, so fusion takes over. So there probably have been sort of small, very, very fine scale fluctuations in core temperature in the sun that have allowed for fusion to take place at slightly different rates. But there's sort of a feedback loop that keeps the sun from going crazy, blowing up, or collapsing in on itself and forming a black hole. It's, again, because gravity and fusion are creating these equal but opposite forces. So the way that this thermostat works is by having temperature be controlled by gravity. Gravity controls the temperature because it controls the density in which all of these particles are in. So when gravity takes over and it crunches inwards a little bit, then you drive up temperatures. So if gravity controls temperature, temperature also controls the rate in which fusion happens. And the rate in which fusion happens controls the external expansion of the sun, that outwards pressure exerted from fusion. So you have this balance in play. It's a wonderful, naturally occurring thermostat. And the result for us is having a source of energy that is so consistent, so stable on the surface of the Earth that it allowed for life to evolve. So the next thing that we're going to talk about, specific to our sun, but utilizing information that we can then apply to other objects out in the night sky, is the basic structure of the sun. And the way I'm going to approach this is going from as far away from the sun as possible to going inwards. So the very last thing that we're going to cover is the very core of the sun, what kind of temperatures it contains, what kind of material it's made out of, how it's converting energy, and so on. And we'll start with as far away from the sun as possible and is still influenced by the sun. The first object, if we're going outwards and going in, is the solar wind. It's not really even so much a tangible object. The solar wind is this material, in a sense, that's slung out from the sun out in all directions. So we already know that the sun shines, and it shines light on every corner of our solar system. In addition to this light that's actually visible, it's in the visible light spectrum, it also slings off all these charged particles, sometimes increasing in the amount of those charged particles that are actually kind of slung out in all directions. The stream of charged particles that has been emanating from the sun, we think, since the sun formed, is called the solar wind. And the solar wind has a direct result on conditions on the surface of the Earth and the other planets. Given free access to the atmosphere of a planet, these charged particles would actually be capable of stripping away a planet's atmosphere. Those charged particles could attach themselves to these gas molecules and could just remove them from a planet's atmosphere. We think that's what happened to Mars. Mars, having lost its magnetic field billions of years ago, allowed the solar wind free access to its atmosphere, and that atmosphere was slowly stripped away. Our planet still has a magnetic field, and for the foreseeable future, at least another billion years or so, it will continue to have a magnetic field. So we're protected by this influence from the sun, and the only thing that can happen as a result is the really cool light show at the North and South poles. The result of having those charged particles, the solar wind, interact with the gas of the outer atmosphere of Earth. So as we go inwards from the solar wind, a little bit closer to the sun and really part of the sun's legitimate structure, we get to the very, very outer part of the sun's atmosphere, part of the sun that you don't even really consider being part of the sun. So as you get closer and closer and closer to the sun, we still have thousands and thousands of miles to go before you actually get to what you see as the surface of the sun. If you're unwise enough to actually look up into the sky in the middle of the day and stare into the sun, you see, of course, this big yellow ball. And that yellow is really not the outer part of the atmosphere of the sun. It's really the surface of the sun that begins to be made out of something that is not exactly a solid, but it's not really a gas either. This very, very outer atmosphere, only visible were you to cover up the sun and you could see the glow of this outer gas, is called the corona. So in addition to being a beer, the corona is actually part of the sun. It's this outer part of the sun's atmosphere. The middle layer of the sun's atmosphere that begins to be a little bit more brightly colored because it's at a higher temperature is called the chromosphere. This very, very red outer fringe of the sun, barely visible, is the first part to actually be hot enough to be visible in the regular light spectrum. Finally, the surface of the sun is the end of the atmosphere and the beginning of where you have this gas existing more as a really, really hot plasma. And temperatures are only going to just skyrocket from this point inwards. The surface of the sun is where you have this material that's under extremely hot conditions already. The visible surface of the sun, we think, is at a temperature around about 5,830 degrees Kelvin, or 5,830 Kelvin, I should say. Because it is of this temperature, because it's around 5,000 and not 10,000 or 3,000 or so on, that's why the sun is yellow. Because that temperature corresponds to a particular wavelength, this is Wind's law, it is colored yellow. Other stars out there in the night sky are not yellow. They're blue stars or white or red or orange. And it all has to do with the variations in the surface temperature of the object, not core temperatures or outer atmosphere temperatures. So of all of the zones of the sun that we've talked about so far, the most important so far are the solar wind and the photosphere. The next one that's going to be really, really important is going to be the very, very core. But let's get there. As you go into the interior of the sun, things begin to be a lot more speculative, obviously, because we can't travel there directly or observe this directly. But due to our understanding of the way that energy is transported under these really high temperature conditions, we have a little bit of an understanding of how energy is transported away from the very, very hot core and out to the surface and beyond the surface. As you get close to the surface, heat and energy is converted up to the surface, moved through convection. Very, very similar to the way that heat is transferred in the interior of the Earth. Hot material and hot gas rises up to the surface, cold material sinks back down to replace it, like a convection oven, convection in the atmosphere, convection in the mantle, and so on. This is just heat transfer by convection. And that's how energy is going to be converted from the radiation zone out to the surface and then eventually beyond the surface. Inside, within the surface of the sun, even more, getting closer and closer to the core, you have the radiation zone. Essentially, temperatures are too hot for there to be actual material that you can convert around and move around through convection. Convection actually requires a gas or a solid or a liquid to actually move up and down. The radiation zone is all about having pure energy converted and moved away from the core and out to the convection zone. So it's energy converted and transferred through photons. Again, because you have an increasing temperature as you get closer and closer and closer to the center. The 10% of the sun that is most centralized is under the highest temperatures. And the 10% of our sun and the 10% of other stars that are like it is the part of the sun that is hot enough to go through this process of nuclear fusion. So this, therefore, has to be the most important part of our sun and any other star. This is where the heart of the star is, essentially. If you think of our heart as being the most instrumental part of what keeps our body going, the fusion that's taking place in the core of the star is essentially like the heartbeat of the star. Without it, the star collapses in on itself, explodes. It basically is going to go haywire and it's not going to be stable anymore. The core of our star, and this temperature is going to come mainly from the rate in which fusion happens, and a calculation involving the rate in which fusion happens and counting neutrinos. The core of our star is thought to be 15 million Kelvin. So that's, to give you kind of a corresponding temperature, temperatures on the surface of the Earth rarely get up above maybe 270, 300, maybe 350 degrees Kelvin. This 15 million Kelvin is conditions that we never ever see naturally occurring on the surface of the Earth. This is where fusion happens because temperatures are high enough, and fusion is the source of all of this energy that's moved outwards out to the surface of the sun and then converted out into pure energy that travels through space. And the only thing that can travel through space is really the light, and that light is then transferred into heat when it gets into our own atmosphere. So to give you a little mock-up of what's going on with temperatures the whole way, the surface of the sun is almost sort of tepid in comparison. It's almost sort of lukewarm in comparison. The surface of the sun is a mere 5,830 Kelvin. Then from the surface of the sun, going through the convection zone, through the radiation zone, and into the very core, just skyrocket up from 5,830 Kelvin to 15 million Kelvin. In high mass stars, this core temperature is 10, 20, 30 times that of the kind of temperatures that you might get in the sun. And there's going to be sort of a lower limit of around maybe 3 to 4 million Kelvin of what kind of conditions you can actually have fusion taking place. So again, that's the most important thing going on in our sun. That's the heartbeat of the star. The last thing I wanted to talk to you about with regard to our sun is the kind of intermittent solar activity that we get. All of these really cool things like coronal mass ejections that might relate to an increase in the amount of auroras that you're able to see on Earth. This picture I have here is a picture taken in X-ray of the event that's happening on the surface of the sun that corresponds to some of this increase in solar wind activity and the increase in subsequent activity in the outer atmosphere on our planet. The reason why it's taken in X-ray is because it would be completely invisible were it in some other spectrum of light. Let's say the visible light spectrum. In visible light, all you would see with these sort of outwards columns of gas rising up off the surface of the sun would just be a dark part of the surface of the sun. All you would really see would be sunspots. All of this solar weather, solar activity that's intermittent, basically happens because of the sun's magnetic field. And the sun is capable of producing a magnetic field because parts of the internal structure of the sun are made up of hydrogen that is so dense it exists in a metallic state. So essentially, we think that the sun has this magnetic field largely for the same reason that Jupiter has a magnetic field, because you can get this hydrogen under really high-pressure, dense conditions to conduct electricity. So the sun, Earth, Jupiter all have a magnetic field, and they all work under sort of slightly different ways. A magnetic field under sort of natural conditions has this smooth sort of dipole structure. On Earth, that structure, for the most part, under nice conditions, runs out of the South Pole, largely close to the South Geographic Pole, and into the North Geographic Pole. So that's what it is to have a dipole structure, like a refrigerator magnet would have a dipole structure. Invisible to us are all of these magnetic field lines that run out of the south and into the north. So under some conditions, our sun has this smooth structure, one big dipole where all of those magnetic field lines go from the south and into the north. Through an 11-year cycle, the sun's rotation causes the magnetic field to get kind of tangled up so that these field lines don't run smoothly out of the south and into the north. Instead, they sort of start to run haywire. They start to run in and out of the surface of the sun, spread across maybe its equator, spread across its surface. These little loops in the magnetic field are going to be tied back to places on the surface of the sun where conditions are a little bit colder. And those colder conditions are going to correspond to dark spots on the surface of the sun, or sunspots. So the occurrence of sunspots, coronal mass ejections, solar flares, solar prominences, they're all really going to be tied back into the same thing. And it's this 11-year rotating cycle where the sun's magnetic field starts by being really smooth. It gets kind of tangled up over time, and then it reasserts itself in a smooth dipole structure, basically sort of clicks reset and starts over again. The sunspots are going to look in visible light, not that impressive. These were features on the sun that Galileo originally picked up, and he was just basically sort of picking up at imperfections and seemingly perfect objects in the universe. These sunspots increase in abundance until you sort of reset that 11-year cycle. And now what we think, if you take and look at these sunspots through another type of light, mainly X-rays, you can see how those are really just magnetic field lines running out of and into the surface of the sun. Whereas most of the surface of the sun might be 5,800 Kelvin, the area right around these sunspots is a lot colder, maybe 4,500 Kelvin. And that decrease in temperature is just enough to cause the light to go out. Kind of like missing a pixel on your computer screen. That would be the equivalent of these sunspots. So 4,500 Kelvin is where all the bright spots on X-rays show up, where you see all of that gas shooting out of and into the surface of the sun in X-ray. That's going to correspond to the dim little sort of almost kind of missing pixels when you're looking at it through visible light. So solar flares are essentially, for our purposes, just bigger versions of these sunspots, essentially. These little loops in the magnetic field line. Sometimes you shoot off a lot of gas all at once, and this picture is taken in UV, right? So it's a slightly bigger wavelength of light than the X-rays. The solar prominences are even bigger versions, and those solar prominences, these giant loops in the magnetic field, can sometimes give off these coronal mass ejections, basically where lots and lots and lots of matter is actually streamed outwards from the sun. Lots and lots of matter is then slung off into space, and it's mainly when you have one of these big coronal mass ejections that people in really, really far northern latitudes on Earth and really far southern latitudes on Earth start looking up into the night sky and expecting to see the auroras. Because with these big coronal mass ejections, you have a big peak in the intensity of the solar wind. Lots and lots of charged particles that get slung towards Earth. Those charged particles harmlessly make their way around our own magnetic field to then play a cool game with the gas of the outer atmosphere and create the auroras. So we're extremely lucky. We have this magnetic field that protects us on Earth from these charged particles. But it would be a really, really bad day to be on, let's say, Mars, for instance, when they were having a coronal mass ejection on the sun. So that's all we're going to talk about with our sun specifically. We're going to tie everything that we did talk about in terms of our sun to the, we're going to talk about everything in terms of our sun and be able to sort of apply it to other stars, stars that are more distant from us, stars that are in obviously completely different solar systems, even different galaxies. By understanding our sun and applying what we have to other stars, we can then, take this really sort of step further. The last thing I wanted to show you is just a little bit of footage from NASA. Last year, they put together this incredible 4K footage of the entire sun, taken in many different wavelengths of light. So I'm going to let you just enjoy that for just a minute. So as these charged particles stream past our own planets, they harmlessly just get entangled in the magnetic field of our own planet, making their way towards the poles where they can just create a cool light show with the gas of the outer atmosphere of Earth. So the last thing I want to mention is the importance of being able to view the sun and other objects out there in space in not just the visible light spectrum, because so much is concealed to us when we're only looking at the sun through visible light. While we look at the sun only through visible light, all we see is the yellow surface of the sun and those sunspots. But when we look at the sun with all of these different wavelengths of light, in UV and infrared and X-ray, then we reveal all of these cool processes that are going on with the force of fusion and with the whole process of these magnetic fields looping in and out of the surface of the sun and creating all of these cool bursts. All right, so we're going to then apply everything that we talked about today in terms of our sun and how we understand our sun to all of the other stars out there. We'll begin to classify and categorize billions and billions and billions of other stars out there in the night sky, and to be able to understand them, but only because we're sitting on top of our own sun and we can use it as a comparison. So the next lecture is all about classifying stars. Until then, keep looking up.